Alright, in the previous video I had taken you through how to calculate the velocities and the time. The velocity here specifically is related to the reaction time. Now, one of the problems here is that it locks us in so that if I change this time increment, for instance, I would have to change how far I extend this formula and how far I extend this formula. The nice thing is that if I do make a change like that, I can fix it. So for instance, now I need to scroll this back a little bit, so I can go back here, click this, and drag it up to 0.5. Okay? So it is doable. It's just not necessarily ideal in terms of how this works out. So how can we make the position be responsive to all of this stuff? So the question, if that's the question, then the answer is we need to relate our position to the velocity, which should be pretty easy. So I'm just going to make use of this formula. So I'm going to use x of t plus delta t is equal to x of t plus v times delta t. And this is, of course, the new position. This is the old position. And our velocity we're going to actually use for x1, or position 1. We're going to use the velocity that it has right at that moment. This is, of course, wrong. We should be using the average velocity. But because we're doing this incrementation setup, we can kind of get away with it. And particularly if we had very uneven acceleration, so the acceleration was changing over time, we would definitely want to use this type of a setup rather than try to figure out what the average is for something that is maybe spending a lot more time going slowly and then speeds up suddenly, that type of a thing. So this is what we're going to do. It's going to look very much like the velocity equations did. So I'm going to do equals, and I'm going to say the position above it. So this is the previous position value. I'm going to add to that the velocity at that time times money B, money 1. So the time incrementation, where the velocity times the change in time is equal to the displacement. So if we are going 25 meters per second for 1/10 of a second, we should go 1/10 of the 25 meters that you would go every second. And if I scroll that down, you can see that that kind of persists. Through half a second, we go half of 25 meters. Once we get past that, it starts to look a little bit different. Because our velocities are changing now, we're not traveling quite as far as we had previously traveled during every 0.1 second increment. And I can once again do something very similar here, as I did for the velocity. I can just take this, copy and paste it over here. Now what this does, you can see that the h2 is the previous value for the position, and the f3 is the current velocity value. So I set this up intentionally with velocity 1, velocity 2, position 1, position 2, so I could just copy and paste formulas, because I'm lazy, and spreadsheets help me be lazy and still come up with solutions that I like. So this is what we get to then. So we have this as our position graph. Now what I'm going to do is I'm going to graph these two quantities, these position quantities, because what we're probably most interested in is whether or not these cars actually hit each other at some point or get really dangerously close to each other. So let's go ahead and plot this. Insert. So I'm actually clicking the insert button that's up here. You can't see it, but if you look at your Google Docs spreadsheet, which hopefully you're doing along with this, you will see it then. And I'm going to insert a chart. Okay, now it wants to be not helpful at first. So the first thing we need to do is figure out what kind of chart we want. All these go scatter. Okay, and then what we can do is we can actually change this to be, you know what, I actually want time and these two position things here. And it looks like it's not actually going to let me do that. So I'm going to try something else. Insert chart. This is one of the downsides of Google Docs. The chart feature is not spectacular. So I'm going to select my ranges a little bit here. So I have that. I'm going to add another range, which is going to be this segment here. Now I should be able to get this to work in a sort of nice fashion. There we go. So once again, scatter plot. I'm going to use row 1 as headers, so hopefully you can see here, oops, that position of car 1 is the blue one and position of car 2 is the red one. And I could do a better job labeling these things. This is position, oops, customize. Technically this should be position versus time of two cars. The more descriptive the better. Our axes should be time in seconds on the horizontal axis, and our y-axis should be position in meters. Okay, so I'll go ahead and I'll insert that chart. And the reason why this is nice is because now we can start changing some things and we can see the result that those changes have. So I'm going to obscure all the numbers now and we'll just see what happens. So I'll leave the reaction time the same, but let's say that both cars now accelerate at -4 meters per second every second. And this is a reasonably high braking acceleration. It's not maxing out the brakes, but it's about halfway there, probably a little bit more than halfway there. And so we can see that they started only 10 meters apart, which in car time, moving 25 meters per second is actually a lot. And you can see with that half a second reaction time, we end up getting them quite a bit closer together than we might like. We can also do some more changes. What if they're going faster initially, right? So let's say that they're both speeding quite a bit. And we can see that now the position of car 1 is even closer. So it's probably cut this down to about 5 or 6 meters of separation, which is cutting it awfully close. Most cars are not excited about that prospect. So then what we would get is maybe this car, once he realizes he has to stop, he brakes really hard. This really comes into being a problem if there's a car behind him who's also following him too close, and then he's going to want to overreact as well, and we eventually very, very soon max out the acceleration that's possible by the brakes, which is generally around -7 to -8 meters per second squared if it's a dry road. If you can't actually achieve much more than this, or if maybe he's got worn tires, so maybe it's a little bit slick outside and he's got worn tires, now we're getting really, really close to an accident with these situations. So one of the nice things here is that we can play around with this stuff and see what are the ramifications. What if he's following even closer and he's only about a car length behind? Well, now we have a collision that occurs. And even if we have it so that he accelerates reasonably fast at about the same rate, he's quite possibly going to bump into this other car. It's going to be very, very close. So in the next video, what I'm going to do is I'm just going to show you a better way to incorporate the reaction time, because this is actually one of the most important factors. If the driver in car 1 is not paying full attention or is just not able to react as quickly as we might hope, then we could get into a lot of trouble very quickly.